Hi, this is my 6th devlog, and I recently overhauled most of the physics in my game. A common problem in games is locking the physics to the frame rate. In Unity, this is generally solved by multiplying all movement by time.delta time, which is the time since update was last run. This works for single states, like walking around on a flat plane, but when your player can enter states where the script does something different, this can lead to problems with consistency, where running back the same exact input with a different frame rate can give different results. Here's a visualization of what happens when I use a raycast in update to check if the player should fall. If I set the frame rate really low, you can see the problem. Now the player doesn't start falling until update runs, but they keep moving since the physics runs independently of the frame rate. At 60 FPS, this is really difficult to notice, and my slow motion script didn't decrease the number of times the raycast was sent, so I didn't notice this problem until the overhaul. The correct solution to this is to move all the physics-based code to fixed update, which runs a set number of times a second as long as your frame rate isn't in the low single digits. So the physics are now consistent, but if there are multiple frames rendered without physics updates in between, the objects don't move. This causes stuttering as multiple frames show the object in the same location. The standard solution to this is to add a rigid body to all moved objects, set them to interpolate, and use rigidbody.move position every time you move them in script. This works fine as long as your movement is in fixed update, but I would like a way to avoid the performance hit of adding rigid bodies to everything that moves. My solution to this is to add a static script to interpolate movement. This class has a public, static function all physics objects will call to add themselves to the interpolated objects list. This will record their current local location and rotation, their parent, and a reference to the object's transform. Every fixed update before physics or any other scripts are run, this script runs. It starts by checking if an update has run since the last fixed update. If so, the location and rotation of every object we're tracking has changed in update, so we'll have to restore the last fixed update location and rotation since we don't want the interpolated locations we used to make things look nice affecting the gameplay. Next, fixed update runs in every other script, which is where we have all the code-based movement. Then, the physics engine runs. These three things run in a cycle, 50 times a second, regardless of how many frames are rendered. In a separate loop, update runs for every frame rendered. Every update before any other scripts run, a frame interpolation factor is set to the percentage of the way this frame is in time between the last fixed update and the next. Then, if there was a fixed update between this update and the last, the local position and rotation of all objects are recorded so they can be restored in fixed update. This records the effects of other scripts' fixed update running and the physics engine. Next, every object has its local position and rotation set to the interpolated value between its most recent fixed update position and the one before that. This means every movement in the game is displayed one fixed update cycle after it happens. So the value at 4 milliseconds is displayed at 24 milliseconds because we need both the 0 millisecond and 20 millisecond locations in order to calculate it. This isn't great, but the only alternative to interpolation I know of is extrapolation, which would cause a lot of problems as the game misguesses where each object is about to move. Just for my benefit, Update also displays this square the first update after a fixed update, so when I look at gameplay frame by frame, I can tell when a fixed update has run. Earlier, I mentioned using local location and rotation. This is what the game looks like if you use global location and rotation. What causes this is that the game updates the objects in the order they were added, so it might move this foot, then the lower leg, then the upper. Each part is moved to the correct location, but moving a parent can mess up its child. I could sort things by their hierarchy so they don't affect each other, but using local data solves this problem too, and I have yet to calculate the efficiency difference of the two approaches. The parent I record for debugging purposes. In fixed update, I check every frame if the parent has changed and log a message if it has. This should never run because I have a change parent function which should be called every time that happens. But I'm going to keep checking throughout development because missing a parent change causes the object to be in the wrong place for 0 to 2 frames, which is easy to miss. Calling change parent records new location and rotation data, so update doesn't use any data relative to the last parent, which would basically be a random location. This system is rather simple, but it took a lot of research and trial and error to get right, so I thought it was worth explaining concisely in a video. Also, if you aren't willing to lock your game to a frame rate, a system like this is mandatory for a game to be consistent, so it's weird how few tutorials there are for this kind of thing online. Another thing I found while building this system is that inputs are only processed in update. If you grab inputs in fixed update, you'll get duplicate button presses. I don't know if Unity changed this recently, but a lot of forums online get this wrong. One possible point of confusion is that button inputs are processed before update and axis inputs are processed after update for some reason. So if you look at the inputs over time, a joystick movement will be reported first in a fixed update and the following update will show the same value. But if you have multiple fixed updates in a row, they will all have the same value, and multiple updates in a row will have different values, showing that that is where they are read in. Another interesting change from this month is that I switched my multi-array based systems to a single array of a custom class for managing math blocks, which I should be covering next month. Efficiency is going to be a real issue in my game. Logic circuits have to update the mesh and run calculations on every gate every other frame, so how I store that data is important. Dictionaries and dynamic lists are both less efficient than arrays. I believe that's general knowledge, but something I did not know is that storing data in a single array of a custom class rather than in multiple arrays is just as efficient. It is, however, much easier to read, which is the main reason I used it in the past. But if you make multiple reads or writes to the same instance of the class, copying the instance you want to reference into a local variable makes read and write operations more efficient than directly editing the array entry, since you don't have to use the item's index in every call. Also, in C# at least, doing this creates a reference to the array entry, not a copy, which confused me for a while the first time I encountered it. Anyway, hopefully this was helpful to someone. I certainly could have used a better explanation of update and fixed update a few years ago. Next month, math blocks. Sounds exciting, right? See you then.